Okay, question number 1. It asks you to provide a complete curved arrow mechanism. To get an alkene. Okay, to get an alkene. This is an alcohol. You get an alkene. What happened is elimination. Basically, you eliminate an OH and a hydrogen on the beta carbon. Okay, this is the alpha carbon. Either one of these are beta carbons. Again, you may not or you may have not seen this reaction before in the class, but it did give you the starting material and the product. All you need to do is use the knowledge you did get from the class and see what happened. From here, again, the OH is gone. You have a double bond between two carbons, means what? There's hydrogen is also gone. Means what? You literally take water away from the bond. Do you guys see that, everyone? We did learn the reverse reaction, actually. But what is the mechanism? Under acidic condition, okay, under acidic condition, if we want to take an OH away, we know OH is never a leaving group. We did learn elimination, by the way. This guy, elimination, can either be E1 or E2. Do you think it happens via E1 or E2?
E1.
E1, why? Because we don't have a strong base. This is even what? Under acidic condition. You guys see that? So it is E1, not E2. Again, E2 we need a strong base. E1 means what? The leaving group leaving first. What is the leaving group, guys? What is the leaving group? The OH is leaving group. Now we learned, is OH a good leaving group?
Then carbon?
No, right? It is OH is the leaving group. But OH is a terrible leaving group. Why? Because if OH leaves as a what? As OH minus. It's never gonna happen. So, in order to make OH a leaving group, the first step is the oxygen grabs a proton. Because you have what? You have concentrated sulfuric acid. After it grabs a proton, this guy becomes what? OH2 plus. Now OH2 plus can now be a what? Good leaving group because it leaves as what, guys? As water, neutral water. You see that, guys? After this leaves, we have what? We have what? We have a tertiary carbocation. You guys see that? Now, if you have a tertiary carbocation, the second step is very fast. Is any base, in this case will be water, takes a proton from the beta, give you the product. That's it. Does it make sense?
It doesn't explain, but how to get there? Like,
Because again, you need to ask yourself what happened. This happened is what? And water is removed. Water is removed as what? OH and H. So that's elimination. If it is elimination, it happens either E2 or E1. We'll only learn E1 or E2. This is E1. Why? Because we don't have a strong base. If we don't have a strong base, this has to be E1. Now, in order for OH to leave, we said OH is not a good leaving group. You can check the slides. OH is a terrible leaving group. Why? Because OH minus is not stable. It's a strong base. We don't want a strong base. Living groups are all weak bases. We learned living groups are what? Living groups are conjugate base of what? Strong acids. So they're all weak bases. So in order to make OH a good living group, I need what? I need this to be pronated first.
So how do I assume that water leaves?
If OH, I think I asked you to make a note when we talk about this. If OH never ever want to be a living group, it has to be pronated to become what? Water. To leave as water.
I forgot about it.
Okay, to leave as water. That's why you need acid, concentrated sulfuric acid. And the second step is whatever base, most likely water, takes the proton from the beta, get the double bond. Does it make sense? Okay, second question. Now we use a what? Again, guys, I'm showing this multiple times. Okay, we use what type of base? A bulky but what? Strong base. Is that right? If it's a bulky, strong base, this reaction happens to what? What elimination? E1 or E2? E2. Why? Because it is a strong base. Strong base promotes E2. If it's E2, how many steps, guys? One single step. So you draw the proton, draw the hydrogen on the beta. The base takes the proton, make the double bond, leaving the leaving group. Done. I don't even need to draw anything. This is done. 3 arrows. This is E2. Okay, this is E1. That's E2. Okay, take a look. I'm drawing the next question on board. You can ask question again. Don't move on yet until you guys are. OTF. All right. Take a look. Again, your test will be the same question asked the same way, different structure. Let me know if you have any questions for this one. Good? E1, E2. E1, see, 2-step. First one, carbocation, then what? Remove. And of course, this one has one extra step because what? Because the leaving group is terrible. You have to make the leaving group a good leaving group. Again, you can make a note here, in case, especially for those of you who are taking 334. If ever OH is going to leave as a leaving group, which happens, OH is always what? Protonated first. So when OH becomes protonated, OH leaves as what? As water. Okay, because OH, this guy is a very poor leaving group. Okay, very poor leaving. Question? Good. Next. We have a structure like this. Okay, structure like this. It tells you this reaction happens via SN2 already. So you don't have to, this question you don't have to worry about SN1 already. This is SN2 already. First, I want to introduce you this guy, OTF. Okay, OTF. What is OTF? OTF has a structure of this. Trifluoral sulfonic acid. Triplet, we call it. Okay, triplet. This is called triplet. Triplet. Now, OTF is a very good leaving group. Okay, first, OTF is a very good leaving group. Why is that? If you take a look, when OTF leaves, guys, OTF leaves as what? As O minus. Is that right? If you're leaving group always leave as what? As a minus, right? Think about, if I have an O minus here, okay, OTF minus means O minus here. This is the TF. If I have an O minus here, what do you think make this a good leaving group? There are a few factors. That's why I said this is a very, very, very good leaving group. What factors can you think of make this guy a good leaving group?
I don't know. I feel like it's stabilized.
Stabilized, right? Good. Well, a good leaving group means what? The charge is what? Stabilized. It's stabilized by 2 factors. The first factor is what? Resonance. We have seen this similar thing before, right? The charge can be what? Can be delocalized to here and what? Here. So the negative charge can be here, and can be here, actually delocalized by all 3. See? And I can draw another resonance. You guys see that? So the negative charge can be delocalized on 3 oxygens. That's one thing, through resonance. Another factor is, take a look at this guy. We have what? Fluorine. Fluorine is a what atom? A very electronegative atom. So the fluorine will try to what? Grab the negative charge across the system, make it what? More delocalized. We call that effect what? The first effect we call it what? Resonance. The second effect we call what? Induction. Okay, inductive effect. Okay, inductive effect. This guy has both effects. First is resonance, second is inductive. And because of that, this guy is a very good leader. Okay, guys, when you study leading group, go to the chart on the chapter 9. Take a look. What are good leading groups? In general, good leading groups are what? Conjugate base of what? Strong acids. Okay, conjugate. That means what? TFOH, or I can draw the complete structure. This guy is a very strong acid. Then the conjugate base is what? Is a good leading group. By the way, we do have this acid. This is that's called tryptic acid. Okay, tryptic acid. It's a very strong acid. So its conjugate base, OTF, is a what? Very good leading group. Okay, this is a very good leading group. So that's what I want to show you this guy because you will see this in your test. Okay, some of you may not know how to analyze. That's why I gave you the structure of it. Okay, this is OTF. What is OTF? OTF has a structure like this. Even though you don't remember what's the structure, you now need to know OTF is a good leading group. Very good leading group. Okay, very good. All right, now, after introducing OTF, let's take a look at this reaction. It asks you to complete this reaction by adding curved arrows and the product and the transition state. Okay, and the transition state. So, first, let's do the easy ones. Arrow. This is SN2, means what? How many steps? One single step. Is that right? So what is the arrow? The arrow is what? The nucleophile attacks the carbon, what? Leading group leaves. That's the arrow, only 2 arrows. What product do we have? How can we show the product, guys? How can we show the product? What type of product do we expect? Inverted. So means what? Originally this OTF is wedge. Now the S sulfur will be what? Dash. Good. The hydrogen is now what? Is wedge.
So why does it have transition state here?
Transition state shows a partially formed bond and a partially broken bond.
So would we have to do this?
Yes, we have to. It asks you to join. This is the product. I'm saying we do the simple ones first. So you first know what happened. SN2 is 2 steps. Wrong step, 2 arrows. And then you get a what? Inverted product. Does it make sense, guys? First, these 2 you have to do it correctly. We have done this multiple times. Okay, this is sulfur minus. Okay, sulfur minus, that means OF. Of course, OF leaves as what? As OTF minus. If you want to see that, just write it as OTF. That's gone. Or, let me show you here. So besides that, you do have OTF minus generated in the system. Okay, that's the leaving group. Okay, that's the leaving group, of course, still in the same solution, but that's the major product. Inverted. Good? Next, what is the transition state? We know this reaction happens in what? One single step, right? One single step means what? Means the transition state involves what? Both. Is that right? That's what we call SN2. SN2 is what? 2 substrates are involved in the transition state. What are 2 substrates? The RX and what? And the nucleophile. So how do we show the transition state? Okay, how do we show the transition state? We know the attack of the nucleophile is from where? From the back of the leaving group. So the best way to show is these two guys, the attack from the nucleophile and the leaving of the leaving group are the opposite, because they are attacking where? From the back. So the easiest way is I rotate this guy. Take a look, guys. A little bit in. Make sure this guy points straight down. Okay, let me draw it this way. Again, you can have other ways, but I feel this way is the easiest. If I rotate the OTF straight down, where's hydrogen, guys? Will be still what?
Back.
Still dash. Is that right? How about the methyl? Now methyl will be what? A little outside. Is that right? You guys agree? Now, it's easy to show now. The nucleophile now, S minus, has to what? Has to partially attack, and this guy is what? Now what? Partially broken. See that? That's the transition state. Of course, after this, the charge will be partial minus, this one partial minus, this is partial plus. If you want to show the charge, you don't have to. Okay, because we have now a partially what? Formed bond and a partially what? Broken bond. And in the transition state, we have how many species? 1 and what? 2. That's what we call this what? SN2. Okay, SN2. That is the transition state. Does it make sense? Okay, again, transition they just show you what happened in the reaction. Okay, why is SN2? SN2 because in the transition state, we have 2 products involved. Yeah, I'm sorry, 2 species involved. Does it make sense? Okay, that's it. That's the first question. Good?
This might seem kind of dumb, but for the product, since it's inverted, does that mean the OTF is inverted too?
OTF is gone. OTF is the leaving group.
Then why did you write it in the product as TFO?
This is one of it because leaving doesn't go away. It's still in there. They're together. Just now they're two. So this is the product. We call this the byproduct, if you want to say.
Okay.
Does it make sense?
But is
The
it?
leaves, they're still in the same. If we do the reaction in a flask, for
Yeah,
example.
it would be that plus that.
Yes,
so-
plus that. I mean, you don't have to show it. I'm just showing her to show you, hey, this guy's still here.
But is there a reason that you wrote it, like flipped?
Which one? Here?
Yeah, as TFO instead of OTF.
Oh, they're the same. OTF, TFO is the same
Okay,
thing.
it's just.
Yes, I mean,
Okay.
just you just turn it back first.
Okay.
Yeah, it's the same thing. Yes. Anything, please, feel free to ask. Okay, I want to clarify everything for a second. And also, kind of review what we learned. Again, you only learn when you do the practices, using the ones we learned we did in class. Questions? Good? All right, next question. I want to ask you, you tell me the answer. The carbon undergoes inversion. Is which one? Is this one, right? What type of carbon it is? Secondary, because you have hydrogen, that means what? 2 group on it, so it is a secondary. You guys agree? Okay, very good, secondary, you circle the secondary. Circle the solvent in which this SN2 reaction has the fastest rate. Which one do you think? This is SN2, so what type of solvent does it need? Polar A product, is that right? Out of these 5, which one is polar A product? Hexane is polar? Hexane is not polar. What are polar A product, guys? Take a look. Huh? Say it again? The third, methanol? Methanol is product. Methanol has OH. See, you guys, that part, the reason I ask you is that you guys didn't learn this, I mean, at least didn't review this part. Solvent is very important. Like I said, you don't have to memorize a lot of solvent. Those are the ones in the chart, in my slides. What are polar product solvents? I'm sorry, polar A product solvents we use. Guys, take a look. DMSO, DMF. We have 4 of those, right? In your chart. You don't have to really look for more. Just the one in my notes. They give it to you. We did it in class. What are those most commonly used polar A product solvent? DMF, DMSO, and what? See, you even didn't study my slides. How would you study the?
I studied so much, you can't remember everything. It's way too much.
I know.
Focusing on mechanisms.
No, hexane is non-polar. Polar A product.
Is it water?
DMSO, DMF, or are they? Come on. 2 more. Acetone and acetylnitrile. Okay, acetylnitrile. Those 4 are polar A product solvents. So out of these 5, which are polar A product, guys?
Acetone and DMF.
Acetone and DMF.
So you can do both.
If the reaction asks which one is fastest, I look at the one which one is more polar. In the chart, which one is more polar? DMF. So I will say DMF. But the keys I got from this question, says acetone. I don't know. Both are fine. If we really want to do which one's fast, I would say do the experiment. Choose both solvent and wrong. But both are fine. Okay, I will choose the one which is more polar, DMF. But the key I got from acetone, which I can explain. All right. But as long as you choose a polar A product, that's fine. Okay, that's I mean, the rest of it is experiment. We haven't done the reaction. We don't know. Some things we do not. Does it make sense, guys? As long as you don't choose the other 3, the other is impossible. Okay, these are the other 2, methanol and ethanol. They're what? They're polar product solvents. Hexane is what? Hexane is non-polar A product. Okay, hexane is non-polar A product. All right. D. We make few changes and ask you whether the changes cause the reaction to be fast, could be slower, could be cause the reaction to stop, or no effect. The first change is OTF changed to OCH3. So we're changing what? The leaving group. Is that right? We know OTF is a very good leaving group, but OCH3 is a what? Poor or good or regular? Metal? Think about OCH3 leaves as what? OCH3 what? Minus. Is that right? Is that good leaving group or bad leaving group? Very bad leaving group. Why? Because the O minus, can anybody stabilize it? No. Is that right? You see, we talked about earlier. Is that OH a good leaving group? No. Why? Because the O minus has nobody to stabilize. The same way here. These 2 are very similar leaving groups. Terrible leaving groups. As a matter of fact, this guy never leaves. If you want to leave, you have to what? Pronate. If you pronate, the reaction can never happen on SN2 anymore. So it is a very bad leaving group. If that's the change, the reaction most likely will stop. At least if you only change that, even you use good solvent and use this strong to follow the reaction will not happen. Does it make sense? The reason is this leaving group is terrible, terrible, terrible. Okay, the reaction stops. If you choose slower, I would say still get a correct credit, but the answer is stops. Does it make sense? Next, substrate changes to this guy, OTF. The reaction faster, same, slower, or stops? Which one, guys? This one you can tell. Come on. Faster? It's fine. Don't feel frustrated. It's okay. I don't blame you. I'm just asking.
I don't even know.
No? Think about this reaction is what? It tells you already. This reaction is what reaction? SN2. Is that right? Now take a look at the changing B. What type of substrate we're looking at? What type of substrate we're looking at? P. Is that primary, secondary, or tertiary?
Secondary?
Huh?
Secondary?
Secondary? Tertiary, secondary, or primary? Come on, take a look.
Tertiary.
There are 3 methyl on carbon. Is that right? 3 methyl on carbon, which means what type of carbon? Tertiary carbon. Can tertiary have SN2 reaction?
No.
No. So the reaction what? Stop. Remember, the reaction we talk about is SN2 reaction. Tertiary never have SN2.
I keep, like, then you keep thinking about the base. You forget about the tertiary. It's
Yeah.
like,
Oh
you're
yeah,
thinking
that's
about
why I told you the
nucleophile.
reaction is easy. Too many
like
conditions you have to
no way to
consider.
remember.
So many conditions.
I know.
It's way too much. It's like, I'm thinking about the base now or nucleophile.
I'm
I
thinking
didn't-
about like.
Remember what the change is. You have to ask what is the change. The first one, what is the change? Leaving group. Is that right? The second one, what is the change? Substrate. If it is substrate, you only look at the substrate. When we talk about substrate, we discuss what? Primary, secondary, tertiary, or what? Lilic or benzylic. That's it. Think about when we discuss. There's a table, right? Remember when we talk about table, the first things we consider substrate. Primary, SN2, never SN1. Tertiary, what? SN1, never SN2. Secondary, can have both. Then you look at the condition. Does it make sense? So the second change is about substrate. Then you think about substrate. What is substrate? Primary, secondary, tertiary. Does it make sense? That's fine. Don't frustrate. Like I said, more practice, please. Guys, I know. Only have 2 tests left. This will be more difficult than the final. So make sure you get the best grade you could. Then you're done for the semester. See, you did organic. That's more than most people could do. C. Now we're changing what? Think about it. Like I said, the first change is the leaving group. The second change is the substrate. The third change is what? What's that called? What is the role of the S minus in here, in the reaction? Nucleophile. So we're changing what? Nucleophile. Change from that to that. What about the rate? Think about it. What is the nucleophile, by the way?
How do we know which one is stronger?
Good. That's why I'm asking. How do you know? What is the nucleophile? Which atom is the nucleophile? Guys?
Yes.
The sulfur, right? The S minus. So most likely,
Doesn't change.
this part doesn't contribute much for the nucleophilicity. This nucleophile is what? Sulfur. They both have the same S minus. Is that right? No matter is the lytic sulfur or just alkyl sulfur. There's no real difference. The nucleophilicity is the same for those guys. In most cases, I would say they're the same. So if that's the case, the reaction rate what? Stay the same. Okay, you have to ask what is the nucleophile? The nucleophile is S minus. It is S minus. Does it make sense, guys? Okay, again, you have to ask if there's a change. What is it? Again, you will see similar question in your head. Like I said, if I could give you a practice like this, you will see no practice like this. No matter we take the organic. I don't think in Columbia anywhere give you practice like this because I'm making 2 copies at the same time. Even I copy paste the question. I just change the structure. Okay, I do this answer key at the same time, one by one. It's faster for me. Okay, so please, guys, I know it's hard, but I promise you, if you can pass the class in here, you can pass the class anywhere. I'm very confident in that. If you think about it, you go to Columbia, you have 100, 200 students in organic, unless you go to honors college. Otherwise, the organic classes are around 150 students in the play classroom. You don't even know what the professor talked about in front. Okay, so please, guys, I know it's hard, but don't sleep in the next few days. Number 3. Okay, number 3. They ask you to determine based on the substrate and the condition. Determine the product and tell each product is from which mechanism. This is basically from what? Chapter 9, right? Chapter 9, we learned 4 reactions. They're all competing. SN1, SN2, E1, and what? E2. So they're asking, hey, to determine what path does this one goes and what product will be resulted from each path. Basically, that's what we're asking. If you have 2 products, you have to tell, hey, which one is major, which one is minor. Does it make sense? That's how you answer the question. And here I even give you the hint. Okay, in your test, you won't have the hint. This is the hint. Consider the following. If you have for SN2, all you need is good steric. That means you need what? Primary, followed by secondary, never on tertiary. For E2, you need what? A strong base. For SN1 and E1, you need what? Good carbocation. That means what? Tertiary and secondary, never primary. Primary, you never have SN1 or E1. Why? Because you never have that stable carbocation. And all things being equal, choose the reaction higher up on the above list. That means you consider the SN1 and E2, SN2 and E2 first before moving on. It takes priority. So let's take a look at the three examples shown here. First one, you have what type of substrate, guys? What type of substrate? Primary and a strong base. Is that right? Strong base and strong nucleophile. Very good. Primary, strong nucleophile, and a strong base. What reaction do we have? SN2 and E2. See? Right? Primary. Primary means what? Good for SN2. Do we have a strong nucleophile? Yes. So SN2 and E2. Why E2? Because we have what? Strong base. And we said earlier, on above, all things being equal, choose the one higher up on the above list. So the product, okay, the product here, based on this side. O minus, the product is 1, 2, 3, 4. These two. This is from what? This is from what? SN2. And this is from E2. Which one is major? Huh? SN2 is major. And this is minor. Very good. Again, all things being equal, consider the one above this. SN2 is prioritized then.
Why is SN2 major?
Because substitution rate is faster than elimination in this case.
Okay.
Okay, this is a strong nucleophile and a strong base substitute because it's primary. Okay, substituting is faster. Next one. Okay, the same substrate. Right, guys? We have a what? We have this guy. See, I've shown this guy almost 10 times already. Why? Because not only this guy is good in your test, but this guy is actually very commonly used. This guy is a what? Bulky base.
Strong.
Strong what? Base. Is that right? Bulky base means what?
E2.
Bulky base means it is a what? It's a strong base, but bulky means it is a what? Hinder. Stere hinder means it is a good looking nucleophile or poor nucleophile.
Poor.
Poor nucleophile means the reaction doesn't happen on what? Doesn't happen on what? If it is a poor nucleophile, it doesn't happen on what reaction doesn't happen? If it's a poor nucleophile, substitution doesn't happen. There's no SN2. Is that right? If no SN2, this is what happened what?
E2.
E2. So this is the major product or only product. Okay, only product. E2. See, guys, this reaction shows you what? If I start with the same thing, if I want different product, if I want substitution, I choose what? A less hindered base. If I want an elimination, I choose what? A bulky base. You can control it. Okay, we have a select reagent to choose from. Does it make sense, guys? Okay, they're both primary. Okay, they're both primary. Does it make sense? Okay, next. I have a what? This is what? Tertiary, very good. Tertiary and a strong base, strong nucleophile, right? Ethoxide means ethyl group with an oxygen. Is a strong base, strong nucleophile. If we have a strong base, guys, if I have a strong base, what reaction is promoted?
SN1. Oh, SN2.
SN2, but can this has SN2?
No.
No, because it's what?
Tertiary.
Tertiary. So it's no SN2, but we have a strong base. So what is promoted?
SN1. E2. E1.
E what?
E2.
E2. So the product is E2 product. Okay, E2 product. Only product. You have a strong base. There's no E1. There's no E1. You have a strong base. E1 only weak base favors E1. This is a strong base.
Why wouldn't it be SN1?
SN1,
Yeah.
this is a strong nucleophile, so elimination promotes, unless you have a weak nucleophile. This is a strong nucleophile and a strong base.
Okay.
So there it will be SN1, but E2 happens faster. In this case, you get E2 product. If I change to this guy, if I change this guy to ethanol, for example, methanol, let's say, only this guy, no minus, only this guy, then this reaction will have an E1 and E2. E1 and SN1.
Oh, okay.
This is a strong base, so E2 is promoted. Like I said, when you consider this, always follow the list. If E2 is promoted, then there's no chance for E1 or SN1. Because you have a strong base. Okay, you have a strong base. All right. So this kind of gives you some idea. See, that's how we review the chapter. You guys, after you study, you have to do the practice and ask yourself. Strong base, strong nucleophile. Favors what? SN2 and what? E2. But this guy is a tertiary, so no way you have an SN2. So the reaction is what? E2. Does it make sense, guys? Okay, E2 again, you guys have to know how to draw the product. This is what happens for the E2. You take the proton, make the double bond, and then what? Leave it on the living group. That's why you get it out. Okay, don't forget the product. I didn't show you how to get the product, but all right, next. Okay, question number 4 is relatively easy, right? Is that easy, question number 4? Have you guys tried it?
Yeah.
Okay, I'm erasing this one.
But I don't know.
Okay, I think you can do most of it right. But be careful, guys. Okay, be careful. Like I said, in the test, each question worth a lot more. Okay, it said 3 hash sign. 1, 2, 3. So, 1, 2, 3, 4, 5, 6. 3 hash sign should be this. 1, 2, 3, 4, 5, 6. This is a 3 hash sign. Is that right? React with each of the following. First, react with hydrogen and metal catalyst. And it says hydrogen is in excess, means what? We have a lot of hydrogen. Is that right? If we have a lot of hydrogen, so it means the triple bond will be what?
All the way reduced.
All the way reduced. Very good. Okay, fully saturated. So we get what?
Extend.
That's it. 1, 2, 3, 4, 5, 6. Easy? Number 2. Treat with sodium amide in liquid ammonia. Okay, liquid ammonia.
See?
This one is a little tricky. Sodium amide is what? Is a what? What is sodium amide?
Oh, we
Weak or strong base? this is N minus. So sodium N minus is actually this guy, NH2 minus. NH2 minus came from what? NH3. NH3 is a what? Very weak acid. You can see the pK, this one is very, very high. It's a 30 something. If this is a weak acid, this is a what? Very strong base. So basically this condition is a strong base. Nothing else. Okay, nothing else. If you have a strong base, treating with an internal alkyne, what happens? What happens? Anybody remember?
It's not gonna be alkene.
Alkenes use
It's
sodium
terminal.
E. There's no sodium here. This sodium is sodium plus, not sodium metal.
Ah,
That's why I'm asking. This is a little tricky. This is only solely a base, nothing else. Base only works on what type of alkyne? Alkyne, I'm sorry.
terminal.
Terminal. Is that terminal? No. So this reaction has no reaction. Okay, treating with no, because this is not even terminal alkyne. This is internal. Internal has no proton. This guy can remove. Okay, there are sp3 hydrogens. This is not strong enough to remove sp3. You cannot. Again, this is solely a base, a strong base, of course. Okay, strong base. Nothing else. Okay, nothing else. Okay. Good. Next, treat this one with water, mercury 2 sulfate in sulfuric acid. This is called what reaction, guys? Can we see the condition? Huh?
Oh,
No. What condition? What condition?
oh, acid catalyzed hydration.
Catalyze the hydration. Okay, acid and also this one is catalyzed too. Hydration. Hydration we get what?
Ketone.
We first get
Ketone.
this guy. Is that right? Enol.
No.
1, 2, 3, 4, 5, 6.
Do we need to put enol or?
No, you don't have to.
We could just put ketone?
Correct. This one will what? Will tautomerize 2. But 1, 2, 3, 4, 5, 6. Yes. Now, this is 3 alkyne. Means what? These 2 carbons what? 3 and 4. Is that right? If the 3 and 4 is no matter how you count 3 and 4 and 3 and 4, they're what? The same. You see that? So that means this is sodium product. Even though the OH can be here and here, but you get the same thing. Because this could be 3, that could be 3 as well. So that's why in this particular case, you only get this ketone. But remember, hydration, because these 2 carbons are the same, there's a chance of what? Putting OH either here or there. Does it make sense, guys? This is what you got. Again, you only need to draw this guy, the ketone. I'm just showing you what happened. Hydration. Hydration means what? Add water to the triple bond, you get a double bond. We call that enol. Okay, enol. All right? Next, react with 1 equivalent of bromine. What do we get?
Alkene.
Alkene, is that right? What type of alkene?
With the trans.
Trans dibromo what? Alkene. Okay, very good. 1, 2, 3, 4, 5, 6. Again, trans. Okay, we're learning class. The 2 bromine is trans. Bromine actually has better selectivity than chlorine. Okay, why? Because you started from a what? Like a bridged bromonium ion intermediate, and the other one attacked from the back. So you got a trans alkene. And again, they're asking 1 equivalent. Okay, 1 equivalent. Last one. Treat with HBr, also 1 equivalent. And again, guys, I want to remind you, in your test, it may not be 1 equivalent. You have to read how many equivalent. What equivalent means? The ratio. 1-to-1 ratio or 1-to-2 ratio, it depends. Okay, if I have 1 equivalent, oh sorry, this guy is 2 equivalent. Sorry. 2 equivalent HBr, what do we get?
And alkane.
2 equivalent means what?
Alkene, like bunch of bromine.
You're basically adding what? HBr to the what?
Triple.
Triple bond. And you add how many HBr?
4.
2, right? 2 of it. If you add 2, this addition follows what rule? Mark's rule means the hydrogen will be added what? On the same carbon, the Br will be added what? On the same carbon. So we get what? 1, 2, 3, 4. We get. You guys agree?
Yeah.
Okay, they're at 3 and 4. Remember, your reaction happens at carbon number 3 and 4.
So the bromine's added to the same line because of Mark's rule?
Correct. Marks. Remember, you're adding one at a time. Let's show me the first one. If you after you add first one, you got this. Is that right?
Mm-hmm.
Now you're adding another one. Remember, if you add another one follows Mark's rule, hydrogen will be added where? Here, bromine's there. So that's why eventually you got 2 bromo added to the same. And guys, we actually analyzed here. Let me show you. Okay, again, like I said, we're kind of review. After the first HBr is added, we got what? This guy. Is that right? Then after the first one added, let me show you why we have Mark's rule in this case. This Mark's rule is actually more stabilized than the one we discussed before. After the first HBr is added, if I treat with another HBr, again HBr is H plus and Br minus, the double bond will grab a proton, electrophilic addition. Remember we said Mark's rule, that means this guy have a carbocation, this guy have the proton added. 1, 2, 3, 4, 5, 6. Right? Why we have this carbocation? Because this carbocation is what? More stable, secondary. And also because bromine has lone pairs, actually can stabilize the positive charge. So it can delocalize the positive charge, not just on carbon, but also on bromine. That is why this is preferred. Mark's rule is preferred. Okay, Mark's rule preferred. This is actually, well, you have this same thing in the notes. Okay, just take a look. And I'm just showing you why we have Mark's addition. Then what? Then the other Br minus attacks, give it back. That's why I have 2 Br on the same carbon. Does it make sense, guys? Br has lone pairs. They can stabilize the positive charge. Okay. Okay, again, that's the mechanism here. You take a look at it again. Then I'll erase it and show the product. One, 2, 3, 4, 5, 6. All right. Next. It's a lot, right, guys? I know. Next Monday. First, treat this with peroxide or not?
Yes.
Yes, with peroxide. This is alkene. Treating HBr means what? Adding HBr, is that right? But if I add peroxide, the reaction follows what? Marks or non-marks? Non-marks. Why? Because adding peroxide, the reaction happens through what? No peroxide, the reaction happens through carbocation. With peroxide, the reaction happens through, anybody remembers? Through what? Okay, with peroxide, this is the intermediate. Okay, this is the what is this?
Radical.
Free radical. Okay, bromine is added to the less substituted. Why? Because you get a what? More substituted radical. Okay, more substituted radical. That is why this is the intermediate. Okay, That is why the reaction follows non-Marx rule. Does it make sense, guys? Radical here. Next, treating this guy with, what is it? The structure showing in the question, what is it, guys? What is it? What is it called, guys? The question showing the second reaction, what is it?
CR2.
Nope. What is it called? We have abbreviation, 3-letter abbreviation for that. What is it? Go search for it. I need you to know. I said you don't have to remember the structure, but when you see the structure, you don't need to know. You need to know what that is. What is it? NBS. Very good. Okay, NBS. NBS. Under UV light and dichloromethane, it will what? What happens? Do a substitution of bromine on where? On which carbon? Which carbon?
Beta.
Which carbon?
It's a beta carbon.
Okay, set your notes. Take a look. What happens if you use NBS? What do we use for? We only have one reaction use NBS. Search the note in a second. Wait, where is it? Allylic halogylation, right? Where is allylic? Oh, you said that?
Yes.
Okay, right. So where is allylic?
Either side of the double bond, one way.
Which one? Here, is that right?
Yeah.
And when you get allylic, the reaction happens through radicals, so you get what? A pair of naturals, because this happens through radical. Okay, that's the part. Wedge. Okay, this is wedge. Allylic. Okay, Kayla, could you pause it a little bit? Give me a few minutes. I'll work.